Hello, I'm here to present a brief introduction into the phase transitions, mainly focusing on the Landau theory in context of the Ising model. So, what is a phase transition? It is a transition from one phase of matter to the other. For example, solid to liquid transition, liquid to gas transition, paramagnetic to ferromagnetic transition. Now, the liquid to gas transition is well explained by van der Waals theory. So we'll mostly focus on paramagnetic to ferromagnetic transition and use it to understand the Landau theory as well. To understand this transition, let us start with the Ising model. What is an Ising model? The model states that we have n lattice sites and each site can accommodate either a spin up or a spin down state. The Hamiltonian can be written by this expression. Here, J is the interaction term. So when the spin's anti-line, J has a lower value because we want to respect Pauli's exclusion principle. The Ising model was solved by Ising himself for d equal to 1 dimension. For d equal to 2, it was solved by Onsager, but the solution is pretty complicated. For d equal to 3 and 4, we are still trying to understand it. And for d equal to infinity, we can solve it and the solution is easy to understand. Reason being that we can use mean field approach to do so. So let us try to do this using mean field approach. So in the mean field approach, we assume any particular state experiences an average spin due to its neighbors. Therefore, we define a quantity A, which is the average spin or magnetization in this case, and we write an effective magnetic field for this case and try to solve the expression for A, and we get this solution. So now we'll do it for magnetic field equal to 0 situation. So when magnetic field is 0, if we plot A and tan hyperbolic of this function, we see that the graphs intersect at only one point, and this graph is for beta jqa less than 1, which means above the critical temperature. Whereas for beta jqa greater than 1, we see that the graph has 3 intersecting points, or we can say it has 2 non-zero magnetization values. What this means is we are going from a zero magnetization situation to a non-zero magnetization situation when we are changing the temperature. This is essentially a paramagnetic to ferromagnetic transition, because in the paramagnetic phase there was no net magnetization for the system, whereas in the ferromagnetic case there is a net magnetization. So now let us try to understand Landau theory as well. Landau theory is also a type of mean field theory. It ignores the fluctuation in the system, and it mainly was formulated to explain the continuous transitions. But we'll see that it can also accommodate for the discontinuous transitions as well. So continuous transition essentially means that the order parameter varies continuously with the temperature. So what is an order parameter? An order parameter is a quantity which is 0 after the critical temperature and non-zero before it. So if we just look at the Ising model, we'll see that magnetization was the quantity which was non-zero before the critical temperature and 0 after the critical temperature. So magnetization is the order parameter for the Ising model. So what Landau did was he assumed a quantity called Landau free energy and said that we can, near a critical point, we can expand it in powers of the order parameter. So assuming the following form of the coefficients a of t and b of t, we find that above the critical temperature, the free energy graph has a single minima at 0, whereas below the critical temperature, it has 2 minima. These minima corresponds to the equilibrium states in which a system can reside. Therefore, we can say that the system went from a zero magnetization state to a non-zero magnetization state, because here we have two equilibrium states in which the system can reside and the two non-zero values of magnetization. So this is the same behavior as we saw from the Ising model, and we'll come back to this. Before this, let us try to understand the first order transition. So in the first order transition, if we add odd terms and higher order terms to the expansion, we see the following form of the free energy graphs. The first two graphs are for the below critical temperature region, and the last one is for the above critical temperature region. In the above critical temperature region, we see that there's a single minima and not so interesting solution. But for below critical temperature, we see that there are two minima. One is a local minima and one is a global minima. So suppose a system is trapped in one of the local minima, then it cannot go to the global minima because there's a barrier to cross. Whereas if we increase the temperature, we'll see that the kink or this barrier will reduce, and there will be a point at which the state can move from the local minima to the global minima, and because the state will instantaneously move to the other point, we can say that the transition is a discontinuous one, and thus we can say that we were able to explain the first order transitions using Landau theory. So now as promised, if we revisit the Ising model, we know that for second order, the Landau theory gave two solutions below the critical temperature, and we saw that the Ising model also gave two solutions. From these graphs, we can see that there were two values of magnetization below the critical temperature, and from the Landau theory as well, we see that there are two minimas. That means the system can reside in two equilibrium states, or there are two possible values of the magnetization which the system can have. Thus, we can see that the two results complement each other. Thus, Landau theory can explain this transition very well. So, in conclusion, we can say that Landau theory is good for the qualitative understanding of the topic, but the quantitative results that it provides are not do not match well with the experiments, because the Landau theory ignores the fluctuations in the order parameter. It assumes it to be a constant, whereas we have another theories like the Landau-Ginzburg theory, which one of my classmates will discuss. In this theory, we assume that the order parameter is a function of the spatial coordinate, or we assume it to be a field variable, and that will give us a better quantitative results than this. And there are other theories to understand phase transitions as well, such as renormalization group. But our purpose for today was to discuss mainly the Landau theory of phase transition in context of the Ising model. So, thank you for listening.